Beijing, and thank you for the continue for my second part. So this is our have a rephrase of the title towards physics consistent and controllable general growth. So last time we show the first part, that is Newton gene. This is a physics. Oh, sorry. This is a physics consistent and controllable video generation pipeline, text to video generation pipeline. And then today I will show you the second one, named the SeeU. This is a CPR 2026 paper, and in this paper, we try to we try to build a pipeline for continuous 4D world understanding and generation. So you can check this GIF here. This is a one demo in the paper, in the SeeU paper. So this is the input. The input is molecular sparse frame video or just sparse frames, and our and by SeeU we can manipulate the time and space. How to understand this? That means we can infer the past timestamps, and we can do the in between frame interpolation at any frame rate. We can make this really slow or whatever, and also we can predict the little future, like what is going on, maybe 0.2 seconds later, what is the next, or what is future frames, like that. And we can also manipulate the time or the space. That means we can change the camera pose a little, not too much, because the input is just a really information lossy projection. So so we cannot know everything about the 4D world, about 3D world. So we can only change the camera pose a little, and like here I show the zoom out, so we can see the bigger world here, a bigger world here. Not only the world we have seen, but a little bigger or a little different. Yeah. So I can directly go to this page. Yeah, here. So the same thing for SeeU starts from this slide. We in SeeU we want to answer this question: can we make generative models understand the continuous 4D world? So everyone, I think everyone nowadays they are familiar or they heard a lot about the 4D, about the 4D generation, 4D reconstruction, like that. But SeeU is unique because we not only try to do the only 4D, we try to build the continuous 4D. I will tell you why this continuous is important. Okay. So yeah. So here I show the motivation. I do this small example, like I take these pictures by my iPhone here, and yeah, I threw a cherry. This is actually a cherry, and so you can see the black color is what I have or what I capture by my iPhone, like 0.5, 0.05, 0.15, 0.25. This is the frame I already have. Maybe maybe some sparse frames like this. And for we humans, if we connect these frames, then in our human brain we can actually understand. Understand means we can understand by our high school physical knowledge or something else. We can probably understand the motion trajectory. So I show this in the red color, the trajectory here. This is I call understand. And by this way, we can infer or imagine imagine or guess what is the right location or the possible location for the time we don't capture. Like this is I highlight this color in blue here, so you can see this is position in the trajectory, and this is maybe our imagination of this frame about this time. So this blue color. So we human can do this understanding and imagination or generation in our mind, in our brain, but but the same thing we want to have for machine intelligence. We want to do the same thing for the machine intelligence. Okay, and but yeah, but how? But if we want to do the same thing for machine, it's actually much harder or not so easy because um, because there are some issues when we want to try to build the 4D world. Here I show this high level cartoon figure here. Like for machine vision or machine intelligence, we want to firstly we still need to recover the accurate 3D geometry and some 3D geometry and some dynamical trajectories like the physical trajectories here from our molecular 2D frames. This is not so easy because there are two things. One is a projection. The projection means we only have the few frames from one side, and there are still many so much information missing from this 2D frames. That's still this is a really ill-posed problem to infer the accurate 3D geometry from only a few 2D frames. Right, this is a projection issue, and the other one is remember for most times our camera is not fixed. It's not fixed. That means we may need to move our camera. We need to maybe tracking the moving things. So the camera motion itself will cause the discontinuity about the projected trajectories. So I show this in this for maybe the smooth trajectories in the live 4D after projection, after camera movement, they will look like this. If you connect this frame, if you connect the tracking points along the frame, you probably will get this trajectories. You cannot have anything right from this image, from this projected trajectories. Okay.
So
However,
for the
please.
projection, you mean from 3D to 2D projection?
Yeah. You can understand that. The projection actually means two things. One is a spatial projection, 3D to 2D. I mean, the 3D world, the synthetic 3D world to our camera plane, the UV, the pixel plane. This is I call the projection. Yeah, okay. And the spatial projection. The other thing is the temporal projection because our world is always continuous with the time. I mean, every moment they are actually continuous. But when you capture the videos by our camera, we are not recording the continuous trajectory. We are still build frame by frame. I mean, each frame they have this continuity. So this is why I show the dash line here because we cannot have a yeah. This is how camera works. Okay. FPS. Yeah.
Right.
Yeah. Okay. Then if we if we can left the 2D frames to the live 4D, the continuous 4D, then I can say we can have much better 3D awareness. We can have much better physical consistency because almost for every motion in our real world, they are actually constrained by some really fundamental physical rules, like our energy, like our structure of the our structures, our body structures, our and there are so many things, physical constraints. That means at least for a short range of time, the trajectory in the live 4D is actually really smooth and continuous, really easy, even and are also really easy to describe, right? And also in the 4D we can decouple. We also can easily decouple the world and the camera. We can separate the world and the camera. This is like a motion disentanglement, and also from the synthetic background, not only the moving foreground, moving camera. Yeah. Yeah. This slide shows the method for SeeU. So the method is really straightforward, really easy to understand. We treat this problem. We say this problem could be solved by 3 steps. Step 1, we try to build the 4D world from the 2D observation. This is or also this is a dynamic scene reconstruction, 4D dynamic scene reconstruction. So here we input the monocular frames, sparse frames, and we use some pre-trained method, and we lift by this method we can lift these pictures into the 4D representation. Here, actually, this is achieved by the shape of motion paper. Shape of motion paper, it can build the dynamic 3D Gaussians from a video, from a monocular video. Okay, and remember, after the reconstruction, the 4D world is still discrete in time, because the shape of motion paper, they only build the dynamic 3D Gaussians. I mean, this dynamic means the 3D Gaussians will change frame by frame. So, I mean, in temporal aspect, they're still frame by frame, not continuous. So, so in SeeU, this is our core problem. So our core problem is to try to recover the continuous 4D from this from the reconstruct the discrete 4D. That means okay.
So
That means we
could you talk more about how they live? Is it like
okay.
given one
Yeah,
frame? Is
great.
it like they predict the
Yeah.
depths?
Yeah. Great. Actually, I can skip some details here. Here, I just show you the high level architecture of our work. Later, I can show you more details how to achieve for each step. Okay. I will skip more details. So the second step is our core part. We try to build a continuous 4D from the discrete 4D. And we try to in the continuous 4D we can describe any motions in a continuous way, in a physical way. Yeah, this is our core idea. Then after we have built the continuous 4D dynamics, then we can go ahead. We can evolve the world and reproject the world back to 2D at unseen time and space. That means after we already know what is continuous 4D, then you gave me a time and you gave me a different camera location. Then I can evolve the world according to the continuous 4D dynamics, and I can evolve how it moves, where it should be, where should the foreground be, and then I will project it back to 2D. That means because finally we still need the videos. We still need the 2D frames. So I do the reprojection back to 2D, and this is our project the 2D frames. And there are some missing information, some missing error because we did not see this before. So we do the spatial temporal int context generation for the missing regions. We have the text prompt, we have the partial observations, partial 2Ds, and we also have the in painting mask to tell which part you need to fill in. And we utilize this context pairs, send it to video in painting method, and they will finally give us the unseen frames, the unseen time and unseen space here. Okay, yeah. Then I can answer the questions you have. So let's go to the details here. The first step is to build the discrete 4D world. This is achieved by current method, named the shape of motion. Okay, and so how I did not change here too much because we just need to use this. This is our foundations. Foundations. Okay, I did not to change the method too much, but I can tell you the overall idea. The overall idea is we already have the 2D for the 2D inputs. We can use some pre-trained 2D tracking method, 2D depth method to have the depths, to have the 2D tracks, 2D trackings for the foreground, and also have the foreground segmentation method to mask out to know which part is the foreground, like that. Okay, and then this information will be sending to current 3D reconstruction method. They choose the 3D Gaussian splitting because Gaussian splitting is always quick and photorealistic, really high photorealistic, and yeah, and I mean they have this depths, they have these trackings. Then they can build the 3D Gaussians, and they also left the 2D trackings to the 3D. Then you can achieve this kind of 3D trackings, or say 4D. Okay, I play the video again. Yeah, like this. I can tap down the
So
method.
the input is just a single image,
Yeah.
or
It's a few frames, just like here, a few frames.
a few
It may
frames?
be a few frames, maybe a video.
I
Or you
see.
can just imagine it's a really short, maybe 10 frames video.
Right. Do they
Yeah,
predict the
that's video.
camera?
Sorry?
Do they predict the camera parameters, or?
Yeah, they need. Oh, I forgot. They also need the camera understanding method. I mean, from this 2D inputs, they can extract the camera information. They also need to do that. And this is not end-to-end. This is actually achieved by multiple prior methods. I mean, to have camera parameters, to have depths, to have 2D trackings, to have the segmentations. In that paper, that are also achieved by multiple things. My understanding is why I use that paper, because that paper is really robust for the inputs. So in the 3D or 3D domain, that's so that one major issue, that is if the foreground is not moving, it is not moving so large. I mean, you have not so large disappearity. They are really difficult to deal with, and also there is one another one issue is if your camera is not moving so much. Oh, sorry. If the camera is sorry. So that's actually a similar thing. If the camera didn't move a lot, you cannot have a lot of disparity information. You cannot have a really accurate depths. And also, if the foreground is moving too fast or too large, it is really difficult to deal with that kind of information. So in shape of motion, they solve these two problems by using current 2D foundation models, like the 2D tracking models, like the metric depths, or say the normalized depth estimation for these two things. Then the shape of motion can be applied to all kinds of molecular videos. They are more robust. This is why I choose this.
Right.
I choose this paper for
Is there a
the step
follow-up
one.
work for VGGT or?
It's not a VGGT. It's more old school style.
Oh, I see. But it's
Yeah,
after VGGT.
yeah. Yeah. This paper shape of motion is actually after VGGT, and they have different design philosophy, I guess.
Okay, cool. Thanks.
Yeah. Okay. So this is the step one. We do the discrete 4D world, and the step two is our core part of SeeU, because you can imagine after step one, you can know the tracking points of the horse of the human here, frame by frame. They can give you the 3D tracking frame by frame. But our thing is we need to recover the raw continuous trajectories like here, the continuous line here, the continuous 3D tracking lines here by the discrete points. So when we do this, there are actually two core challenges. One is the efficiency, because here I just show you the downsampled tracking points, but actually the foreground may have 800K 3D Gaussians to represent the foreground. That is a large number, right? That means we have so many Gaussians, the foreground Gaussians, Gaussian tracks to deal with, to learn the continuous trajectory. This is impossible because we cannot have a lot of time to learn the continuous trajectory for each Gaussian tracks. Okay, and the question, the challenge two is we want to ensure the physical consistency. That means your observation or say the discrete 3D trackings, they're actually not so accurate. They may be noisy, and also if we want to predict the future, if we want to infer the past, then we need to understand the trends of the motions, or say you need to have some physical constraints to ensure the predictions they are not so wrong. Okay, they still maintain some trends. So this is I call the physical consistency. And this is our final results achieved by our continuous 4D. So you can see the tracking points is moving along our continuous line here, and the dash part is our prediction. The dash part is the past prediction, and this is our maybe too low resolution. This is our future prediction, and this blue part is our camera pose. Our camera pose is also continuous. Let me replay again. This is our final results, and okay, and I can answer how to solve these two challenges. So for challenge one, the efficiency problem, we solve this by low rank motion modeling. Low rank motion modeling means you can say that you can understand this may be the P may be the position of each Gaussians. Each Gaussian for Gaussian I at time t, its position could be right by this equation, and we decouple this is our low rank motion representation equation. So it could be right by two parts. This part is the initial location initial time equals third initial time for position for Gaussian I, for the Gaussian I here. And the second part is spatial design. So BT here means motion basis. Motion basis. Motion basis means for every Gaussians. So you can say there is no Gaussian I, because all Gaussians they share the same motion basis. This is reasonable because for most of the scenarios the motions or the tracks, they're actually similar, not so far away. So we can say, can we represent the fundamental motion basis for every Gaussians? They share the same thing, but and this motion basis only changes along with the time. They're the same for every Gaussian I, but they will change along the time. And this one also will be manipulated by a coefficient I. Coefficient I, that means this is each Gaussians have different coefficient, but this coefficient they will not change along the time. That means the time they are not changed, but they just change by the Gaussians, by the Gaussian index. So this is a low rank decouple idea for here. In this way, we only need to learn a few Gaussian shared bases, and we also need to learn each Gaussian's coefficient by a few numbers. That's really efficient. Yeah. Do you have any question here?
Yeah, I think we can unmute. Just ask. It's
okay. So is the BT function like pre-trained and then adapts to the like frames that are given?
Yeah. Yes. The BT. So you can say the BT may be these lines. The BT is really simple actually. The BT here is a line-dimensional motion basis. Line-dimensional motion basis. This is not changed by the Gaussians. They only change by the time, and this part is this BT is learned by a small training.
I see.
And okay, and for the second challenge, for the physical consistency, and we solve this problem because we find some smoothness in the motion basis. Remember, the motion basis is already a really low rank or low dimensional things. They maybe have only here I only use 9 channels for the motion basis, and for each channel, it could be plot. It could be plot like in the discrete points. Yeah, like the motion basis, it could be plot by this points. The points. If you connect the points, then you can find each motion basis is really simple. It should be a simple curve and smooth curve. Also, the same thing here. You can say the motion basis, the points for the motion basis. If you connect them, they should have some really beautiful smoothness and simple shapes. Then inspired by these findings, we propose to use a BSP line, to fit these discrete motion basis points. So you can say the final fit lines by BSP lines. They are the continuous line I show here. Okay. And the BSP line here is actually a really cheap network, and because you only need to optimize the control points with some our spatial design physical loss or OD loss, it's really efficient, and maybe a few minutes training, that's enough, and you will find this continuous line here. yeah, let's go ahead. And finally, the final step is 4D to 2D, because finally we still show our learn the continuous 4D world by videos or by friends that are easier to play on our phones or our computers. Yeah, this part is is really easy. And remember, we already know the world. Then we already know the continuous 4D dynamics. So we can, for any given time and camera space, we can evolve the world. Then we can project the world into the 2D. So here, here I choose the projected frames. So you can see here, this is our projections. And 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 remember, this projection is not perfect because there are so many missing errors we didn't see before. The camera didn't see that before. Also, the reconstruction may cause some details issue or some distortions, like here, like the around the body of the human and the horse here. There are some issues. Then we can detect this missing error and the issues, and we can say these parts, they need to be imprinted. So by this imprinting masks, we detect these errors. So we have this imprinting masks, and also we can give the prompt here to describe the scenario, to describe the activity, right? And this context information, the text prompt, the projection frames, and the imprinting masks, we send this information into train the video imprinting method called VACE to have the final frame, to have the generated frames here. Yeah, let me replay again. Yeah, then you can see the missing errors, they are automatically filled, and they are really consistent in terms of the semantic or the 3D geometry, whatever. And finally, there's some really some good-looking demos I can show you. The first thing is we can generate the unseen time. Unseen time means we can mirror plane. Unseen time. Yeah, this is the input frames, and the middle one is a visualization of our learned 4D continuous world. And you can see the dash here. The dash part is the predictions for the futures. So in these pictures, so in these slides, I can show you. Actually, I'm showing you the frame interpolation and the frame prediction here. And this is the comparison with other prediction and prediction method. Mirror again. This is the input frames, and this is Cosmos, and this is our method. So you can see the butterfly location. Okay, this is like here, and R is like here. This may be more flat. Our prediction. And yeah, and this is our numerical comparisons. You can say we can do the passive framing inference, we can do the interpolation, we can do the prediction, and no other methods they can achieve this all in one. I mean, current method they can achieve this all in one in a unified architecture. But in SeeU we can do all this, the past, the interpolation, and the future, and this is our best models in this paper. So they can also do the similar thing by some some adaptations like our method, but they are still worse than ours. And the next one, the next big thing is our unseen spatial generation. I mean, okay, let me just play this video. This is the input frames, and by SeeU we can manipulate the camera poses. Yeah, we can do the dually out, dually left, and whatever, and we can always have a really consistent 3D consistent result. And this is a comparison. This is a ICCV best paper we can master. So you can say it loses the spatial consistency of the tree here. Play again. And this is the numbers. So we evaluate the spatial consistency and geometric consistency. I mean geometric consistency by the sorry, I forgot how to read this. In Chinese, 极限几何. Yeah, and so you can say we have a much better, not really much better, but better, definitely better 3D geometric consistency, and also we have a better, we have better semantic consistency by the clip scores. Okay. And one last thing is we don't need to change our framework. We just need to change the prompt. Remember, we just need to we can also see the prompt here, right? Everything is the same. We just need to change the prompt. Then we can do some editing, like the replacement in the prompt. We change the prompt from the girl to the young boy here. So you can see we can do the video editing, and also we can do other things like the objective removal. We just need to remove. We just need to remove the foreground Gaussians in our method and filling the missing backgrounds here. Then you can have the totally clean removal here. And also because we already know we already models the 4D dynamics, then we can achieve the time-lapse effect here, because you can calculate the location of any given time in this video. So you can have the time-lapse here. Yeah, that's it. Yeah, I think that's all for SeeU. Do you have any questions?
Yeah, that's pretty cool. I think yeah, my question, I think maybe you can come back to the assumption there, like for there's an equation for the B. So
this one?
Yes.
Okay.
I think that's the key, right? So for BT, that means you don't assume any objects, right? Like you assume all the motion are the same in the
video? Yeah. The BT is for the trackings, for the discrete trackings to describe the any Gaussian trackings, tracking trajectories for everyone, not specific for someone.
What if you have two objects?
That's still achievable. Let me I can show you some more demos in our project page. Still okay. Multiple. Yeah, like here we have multiple ducks. Oh, I make this bigger. Yeah, multiple ducts. So you can say this is the input, multiple ducts, and this is our learned 4D dynamics, and this is our generated frames. And also, let me see. Yeah, yeah. I think your proposal a really good question because in our method, someone may have some question like if the motion directions are totally opposite in the video, can we deal with that? Like, my answer is it's still okay because we do some experiments like there is a motor, there is a car, they are riding in the opposite time, in the opposite direction. But in our method, we can still deal with these motions, which is not so similar. Can you get my point? Yeah.
Right. If you look at the Starship example, sorry, you just show, right? You just show
Yeah, here. Starship.
Right. So maybe that's not a. I think there was a car, like two people are riding the same car.
Yes.
Here, I think it's soapbox.
Oh yeah, here.
So two people, they're both in the car, right?
Yeah.
They have a similar motions. Like, what if you have if it's like a robot that's like grabbing some objects? What happens? Like, both the objects and the arms are actually moving.
Yeah, they can do that. I have that demo. Let me be here. Future. Sorry, which one? I forgot. Yeah. Here is a robot.
Nice.
Yeah. I mean, yeah. Some people they say because we was assume the BT they are the motions are similar, so we use the BT. There is low I, but actually, when I do some experiments like there are totally two different directions in one frame. We can still handle that.
Right. So maybe I misunderstood the BT. What's the meaning of BT?
BT means the motion basis. You can like here, if you want to describe this motion, right? It's there's so many ways, but BT means you have some basis functions. I mean, you can decouple this actions into a combination. This combination is the motion basis multiplied by the coefficient.
Right, and the
like
coefficient.
XYZ actions, you can combine them and you can finally achieve the exact one.
I see. Is it because the coefficient is also depends on the position?
The coefficient is not. It's only dependent on the Gaussian, the tracking itself, the tracking trajectory itself.
Right. It also depends on I, right?
Yeah. This only coefficient only on the Gaussian I, BT only on the time t. This is the magic part.
Is it for the efficiency reason? You want to use less parameters?
We have to do that because you cannot calculate like 100K Gaussian trackings. That is a waste of the power, the computational power, right? We have to do that. Yeah.
Yeah, it's pretty cool. I think it's and how you feed in the the curve is actually useful?
You mean this curve?
Yeah. Do you need to, for example, choose different basic curve by different videos, or you just use the
We don't
fixed?
need to do that. We don't
Right.
need to do that. Here I just use, in this figure I just use one scenario's BT and its curve and its smooth curve. And like here, this is a curve for the foreground.
Right.
Oh, sorry. This is the curve for the camera rotation, camera movement. This is a 6-channel curve, right? And the right one is a motion basis for the foreground, moving foreground, XYZ. And this is motion basis 1. So in motion basis 1, there are 3 lines, XYZ motion basis. And there are 10 motion bases. I just gave you a random. I forgot the exact number. There are 10 motion bases, and in each motion basis, there are XYZ. Can you get my point? Like here is just a really fundamental things to show. Finally, in each line in the motion basis, you can represent this. You can connect these points by a smooth curve, and they will give you really good performance to model the dynamics, to model the motions, the really complex motions. I mean, really complex motions, multiple objectives, deformations. Finally, you can achieve this. You can model this by really simple smooth lines. Low dimensional smooth lines. That's it. That's a core idea.
I see. Yeah, that's pretty cool. Yeah. Do you guys have other questions? That's it. Sure. Yeah.
And SeeU, my understanding for this project is because we do need to model the continuous world, and we do need to introduce some physical constraints to really model the 4D world, to do the generation or to do the understanding. That is my point.
Yeah, I think it makes sense. So does it have any failure cases?
It's definitely hard. The failure, our major failure is caused by the foundation models, like the reconstruction models. Yeah, it's easy to understand because for some complex scenarios or which may have really complex motion or say really information poor scenarios, like here the leg here is so thin, so the leg the final results will not be good because the lecture is so thin, and maybe the tracking or segmentation method is not so robust for the for this regions or areas. Yeah, and also for these demos, the apple here is too small and moves too fast. Maybe the tracking method, they cannot align pixel by pixel. And also you can see the apple is small, and the apple surface is so similar, so it cannot give you a really accurate 2D tracking pixel by pixel. So you can see the final result is also not so good.
Yeah.
And also our pipeline is I think the idea is okay, but the overall pipeline, because we do this in school, we don't have so many GPUs. So our pipeline is not end to end. There are multiple stage, right? There are multiple stage. This is not so fast. and Google they did the similar thing, named the D4RT or DR40. I forgot the name. Yeah, this one, D4RT. They do the similar things. They teach AI to see the world in 40 dimensions. But in their way, they use they achieve this by an end-to-end architecture. I mean, input here, encoder, decoder, and output. We cannot do that because we don't have GPUs.
Right. Yeah, that's interesting. Okay. Let me start the recording.